In the beginning of this series, The Ancient Secrets of Prediction, we learned how to fit data using a straight line through basic linear algebra. This worked well when the relationship between variables was linear, but soon we realized that data doesn't always follow a straight path. It can bend, curve, and behave in more complex ways. To handle that, we turned to quadratic interpolation, fitting a smooth parabola through 3 data points to capture that curvature. But even then, we assumed that our curve fit the data perfectly. In real-world scenarios, that's rarely the case. Data is often noisy, incomplete, or unpredictable. So what do we do when no perfect curve exists? That's where linear approximation comes in, a practical tool to estimate values locally, even when the fit isn't perfect. Now imagine a factory that takes various inputs and converts them into outputs. Watch how different values are processed and transformed in this system. Before we proceed to solve this, let's try to plot this data. As we can see, the line does not perfectly fit through these 3 points. It has some level of error. We need to find the line that fits best. But how do we define what best means? Let's start by assuming the data points follow a straight line, represented by the equation y equals mx plus c. M is the slope, the change in y over the change in x between 2 points. Let's plug in the numbers. 11 minus 8 on top, 2 minus 1 below. That's 3 over 1, so the slope is 3. Let's see how the slope looks on the graph, starting from flat and increasing until it reaches 3. C is the intercept, the value of y when x is 0. It shows where our line crosses the y-axis. We flip the straight line formula to get the equation for c. Now we find c by plugging in y equals 8, x equals 1, and m equals 3. Calculating, c equals 5. Let's start by calculating the predicted y values using the equation y equals mx plus c. For x equals 1, substituting the m and c values gives us y pred equals 8. When x equals 2, plugging the values into the equation gives y pred equals 11. And for x equals 3, we again apply the formula and get y pred equals 14. Finally, we will plot both the predicted data points and the existing points to visualize the alignment of the predicted line with the given data. However, these predictions may not match the actual values. To calculate the error, we take the difference between predicted y and actual y and square it to keep it positive. We repeat this for each point, and when we add up all these squared errors, we get what's called the total error, and our goal is to make that as small as possible. For the first data point, where x1 equals to 1, the predicted value y1 pred comes out to be 8, and the actual y1 value is 8. So the error contribution from this point is 0. Next, for x2 equals 2, the predicted value y2 pred is calculated to be 11, and the actual y2 value is 11. Here again, the error contribution is 0. Finally, for x3 equals 3, the predicted value y3 pred is 14, while the actual y3 value is 16. The error contribution for this point becomes 4. Adding up the error contributions from all 3 points gives the total error 4. Here, m and c are the parameters of the line, and e is the total error we aim to minimize. Our aim is to find the values of m and c that minimize the total error, e. Now we want our line to fit some points with the smallest error. The steepness of the line is decided by the value of m. Let's see how the error changes for different m values, keeping c fixed at 1. For the first case, with m equals 4, we calculate the predicted y and the value of e, which comes out to be 20. Next, let's increase the slope to 6. The error for this case becomes 14. Finally, for m equals 8, the error is 118. The orange curve illustrates how the error changes with different slope values. As we can see, the best slope is the one where the error is the smallest. Now, let's examine how the error varies with different values of c while keeping m fixed at 1. We'll explore the relationship between c and the error using the same set of data points. When c equals 4, the error for the points is calculated, resulting in a total error of 98. Next, let's try increasing c to 6. The new error is calculated as 59. The error decreases as we adjust the value. Finally, for c equals 8, the error reduces even further to e equals 27. This curve in blue shows how the error changes with different values of c. As we move along the curve, we see the error decrease. You can explore an interactive version of these graphs on Desmos. The link is provided in the description. Let's now combine both plots into this 3D curve showing how error varies with m and c. As we move along it, the attached line shows how the slope and error value e change at each point. This process of measuring change, or slope of our curve, at every step is called differentiation. It shows how to reduce error and find the best m and c mathematically, something we'll use next to locate the lowest point. Here are a few questions to solve based on what we just went over. To sum up, we explored linear approximation, a method used when a simple straight line doesn't quite fit the data. We began by looking at how complex relationships between variables or random noise in the data can lead to this mismatch. Using a factory example, we plotted input-output pairs and observed that the line didn't pass through all points, revealing some level of error. To find the best fitting line, we used the equation y equals mx plus c, calculated slope and intercept values, and compared predicted outputs to actual values. We then measured the error at each point as the square of the difference between predicted and actual values, and added them up to get the total error. We experimented by changing m while keeping c constant, and vice versa, to see how the error behaved. This gave us two curves, showing how error depends on slope and intercept. Finally, we combined both into a 3D surface plot, showing how error changes with both parameters at once.